In this video, we're going to learn about limits of recurrence relations. So first we're going to start with a task. So for the following recurrence relations, which you can see I've given you 4 of them, choose any initial value of your choice and use your calculator to calculate various terms in the sequence. Now for this task it would be good if you did at least 15 terms for each. Now you don't have to be writing these down. Hopefully you've watched the video on the sort of quick method for calculating terms in the sequence using your calculator. If you've not, I would stop this video just now and go and find that from the other day, because that will save you a lot of time here. So putting some values into your into these sequences and seeing what terms come out, and I want you to ask yourself what happens. Obviously, is there something going on with the numbers? Why might this be the case? And could you graph this? Now, probably to graph this just now would be a lot of work for you guys, but it's literally the question, could you graph it? And we can come back and we can chat about what goes on here. So if you pause the video just now, so that you've still got these 4 sequences, and go and try and find some values for this. Okay, welcome back folks. Now hopefully you've managed to do at least 1 or 2 of those. If you've not, don't worry about it. We're going to have a wee look at each one anyway. So the first sequence that I gave you was un plus 1 is equal to 4 multiplied by un plus 1. Now I started off with my initial value being 10. It doesn't matter what you started off with it as. And you'll notice here that the numbers are getting much bigger, and they're getting big very, very quickly. To the point where the Excel spreadsheet that I did this in is having to use scientific notation. So you can see obviously the question what happens is that, well, the numbers are increasing quite rapidly. And why might this be the case? Well, because we're multiplying each of the previous terms by 4, and then we're adding 1, and then we're multiplying that by 4 and adding 1, multiplying that by 4 and adding 1. So we're keeping that going. So that's why it's getting bigger quite rapidly. Now, if I had to graph this, it might look something like this. You might be thinking this is a straight line to start with. It's not. If you look at the intervals on the y-axis, these are really quite large. So you can see that that's increasing, and it will just increase right on to infinity. So that's what happens with the first one. If we look at the next one, with negative 4un plus 1, that was equal to un plus 1. I started off with 10 again, and you can see it appears to go negative, positive, negative, positive. But in actual fact, every time when we get to a negative number, it's becoming sort of more negative, if you like. So the number's getting smaller and smaller every time till we get to that use of scientific notation again. The same is happening for the positive. So it gets bigger and bigger. So what we say is that the values here are oscillating. So it's going between values, and what you'll see here is, see these sort of spikes that's happening here all along as well. It's just I couldn't fit that all into the one graph. So I suppose it brings out quite a nice graph. But you can see that obviously the values aren't really consistent. They're constantly getting increasing, decreasing, increasing, decreasing. Now if we look at this one, the third one I gave you, un plus 1 is equal to 0.4 un plus 1. Again, I started off with 10 being my initial value. Doesn't matter what you started off with, a similar thing will happen anyway. And you can see that it starts getting smaller and smaller and smaller, but to the point where it all seems to be 1.666 recurring. That appears to be happening all the time. And if we then look at the graph, so here's my first initial value, which was 10, and then it went to 5, 3, 2.2, 1.88, and then it almost appears to go into this sort of straight line So that's quite interesting. So hopefully whatever value you've assigned as u0 in your calculator for this sequence, it's ended up that it's got the same value out. The more terms that you calculate, it'll be the same value that will come out. And if we look at the last one, so un plus 1 is equal to 0.4 un plus 1. Again, I started off with 10. And you can see that the graph has oscillated a wee bit here. So it's gone negative, positive, decreasing, increasing, and it does that for a little while, but then you'll notice that all of these values, they're all 0.71 something, and then it becomes 0.71428, and obviously the last digit is changing there, but there'll be more decimal places will come out, obviously the longer you go on. So again, it appears that there's this sort of straight line shape, so that's quite interesting. So what we say is that these two here, the first two we looked at, those diverge because this one, the first one, diverges because it's constantly getting bigger. This one here was oscillating, remember it was going up and down. And we say that the next two, those converge. They converge to a limit. So that's what that straight line sort of effect is. That's converging to a limit. And the same here. And I suppose what we notice then is that the ones that diverge, the coefficient of un here, they were whole numbers. They were 4 and -4. Yet the ones that converged to a limit were decimals 0.4 and -0.4. More to the point, however, these are decimals which, this one's less than 1, this one's greater than -1, however. So maybe that has something to do with it as well. So just to summarise everything that we've done, divergence. So if we have a recurrence relation of the form un plus 1 is equal to aun plus b, and if a is less than -1 or greater than 1, then the sequence will diverge, i.e. it will keep increasing, decreasing, or oscillating. So we've talked about all of those things already. If we have convergence, so if we have a recurrence relation of the form un plus 1 equals aun plus b, where a lies between -1 and 1, so remember we talked about that being a decimal between -1 and 1, then the sequence will converge to a limit. And in the graph, that was when it appeared to go into a straight line, because it settles at approximately the same value. So the more terms we calculate, as n tends to infinity, then the sequence will converge to a limit as long as a lies between -1 and 1. So speaking about the converging to a limit brings us on to talk about the limit of a sequence then. So for convergent sequences defined by un plus 1 equals aun plus b, where a lies between -1 and 1, un tends to a limit L as n tends to infinity. So we've already kind of talked about this already. So the limit L, now if I had to calculate lots of terms in a sequence which I knew converged, so A say was 0.4 like we looked at earlier, eventually all of the values for un plus 1 and un became, it was 1.6 recurring, I think it was. So those all became essentially the same value. They were approximately the same. So if we assign that to be L, so L is equal to A times L plus B. So we're saying, well, that's the limit it's converging to, so all of those terms become the limit. Now, I want to be able to know how to calculate the limit without having to rearrange an equation every single time. So let's try and derive the formula for the limit from this. So if we subtract AL from both sides, so that we've got all of the L's on the same side of the equation, I can then take out a common factor of L. So L bracket 1 minus A is equal to B. And to get L on its own, we need to divide throughout by 1 minus A. So the limit of a sequence is equal to B over 1 minus A. And you can see that B is here and A is here. Now, this is a formula that's quite important. It's not given in the formula sheet in the exam, so it is something you have to learn. So at this point, I would definitely be taking that formula down with the heading, limit of a sequence. Okay, so hopefully you've copied that down in your notes jotter, and we'll go on with some examples. So example 1, a sequence is defined by un equals 0.6 un minus 1 plus 5 with u1 equal to 10. Does the sequence have a limit as n tends to infinity? And calculate this limit if it exists. Right, so part A then, does the sequence have a limit as n tends to infinity? So remember we said that for the sequence to have a limit, the value of A had to lie between -1 and 1. So it does in this case. So we have to say a limit exists as the recurrence relation is linear. Now this is something we have to write every time. I have talked about linear sequences since we started this topic. We're only dealing with linear sequences in higher, so we have to write this in order to get the mark, and we have to write this part as well. 0.6 lies between -1 and 1. So any limit question, folks, any limit question at all, this is always the first mark. Limit exists as recurrence relation is linear, and A lies between -1 and 1, but you actually have to state the value of A so that this is a numerical comparison. So every single time, I can't stress this enough. Now, part B. So calculate this limit if it exists. So we've already said that yes, the limit does exist. So we want to be able to calculate this limit. So we've got our formula, limit equals B over 1 minus A. So that is the same as 5 over 1 minus 0.6, which is the same as 5 over 0.4. Now, I'm going to do this without a calculator just now because a lot of limit questions would require you to leave your answer as an exact value, which is either a fraction or a surd normally. So in this case, it's going to be a fraction. So remember, 5 divided by 0.4 is the same as 50 divided by 4, and that gives us 12.5, which is our limit here. So it would be a good idea to pause the video just now and copy this example down in your notes jotter, and making sure in some way, folks, to highlight the answer to part A and remind yourself that you have to do this every single time. Okay, welcome back. Let's look at a second example. So the deer population in a forest is estimated to drop by 7.3% each year. Each year, 20 deer are introduced to the forest, and the initial deer population is 200. Part A asks us, how many deer will there be in the forest after 3 years? And part B, what is the long-term effect on the population? So we'll firstly look at part A. So we need to define the recurrence relation firstly, because you can see that we've not been given 1 at the moment. So un plus 1 is equal to, now you'll notice that it's a drop by 7.3%. So that leaves us with 92.7%, which as a decimal is 0.927, and we need to multiply that by un. It also tells us each year 20 deer are introduced to the forest, so we need to add on those 20 deer. And remember, to define a recurrence relation properly, we also need u0. So it tells us that the initial deer population is 200. So u0 is equal to 200. Now, we have to calculate how many deer there will be in the forest after 3 years. So we know that u0 is 200. u1 will be 0.927 multiplied by u0, it's 200 plus 20. So putting that into your calculator gets you 205.4 deer. u2 is 210.4058. u3 215.04617666. And it's u3 that we're asked for after 3 years. Now, obviously we can't get 0.04617666 of a deer. So we need to round this. Now remember, it's a real life situation. We always need to round down. So this means that we've got 215 deer. Now, part B, what is the long-term effect on the population? So remember, it's asking for the long-term effect here. So that should lead us into thinking about the limit, because the limit is what's happening in the long term. So I suppose that's key vocabulary here that you need to remember. If you're asked for the long-term effect, you should automatically be thinking about the limit. So the limit exists as the recurrence relation is linear. We've got a statement here, and now the value for A was 0.927. 0.927 lies between -1 and 1. So remember, folks, that's that statement that you write every single time so that you get that extra mark. It's always the first mark in a limit question, so you make sure you write it and you don't lose that easy mark to get. Even if you can't remember how to calculate the limit, you should be remembering this statement, so get that in there every single time. So the formula, the limit is equal to b over 1 minus a. B in this case is 20 and a was 0.927. So the limit is equal to 20 over 1 minus 0.927. And putting that into your calculator gets you 273.9726. That decimal goes on for a while. Now, we need to round this. We are talking about deer, and we can't get 0.9726 of a deer. Now, we don't have 274 deer. So obviously if we were using just rounding in general, we would have 274 deer, but we actually don't have that amount because this isn't a whole deer. So we need to round down, despite this being a 9. So that gives us 273 deer. And so in the long term, there will be 273 deer in the forest. And that's our final answer. So again, folks, a good idea is to copy this down in your notes jotter, and then you can try the assigned exercise.